Okay, this particular problem is going to involve work energy. And we're going to have a potato gun. This potato gun is going to weigh a specific amount of mass. It's also going to have a spring inside of the gun, which whenever the potato is filled, this spring will compress. And so it'll give us a distance of compression, and also we know the spring constant for the potato gun. We're going to position this potato gun on a table that is approximately 1.2 meters above ground level. And this potato gun is going to be a specific angle of 30 degrees. Now, what we're looking for is we're looking how fast the potato is going to be moving when it leaves the barrel. And in doing so, we can work this as a potential energy problem, which will then give us a work energy problem. So, we have the potential energy for kinetic energy is 1/2 mv squared. Now, we look at that and we can also say, well, what about our spring? So, the potential for our spring is 1/2 ksx squared. And what we can do, since the potato is not moving, it has not left, we can therefore assume that the potential kinetic energy is going to be equal to the potential spring energy. So after that spring is actually compressed. If we rework our equation, so what we're solving for is we're solving for the velocity. Exactly how fast is this potato moving when it leaves the barrel. So this component is what we're looking for. And we're going to try to get it by itself. So divide both sides. We're going to get velocity squared is equal to the spring constant times the change in distance squared all over the mass. Square root of both sides. When you square root both sides, this x, this distance changed, can therefore be put outside. So then we have velocity as the potato is leaving the barrel is equal to the square root of spring constant all over the mass times x, which is going to be the change in spring compression. So, you work that out, you'll come out with an answer that will give you the velocity, or how fast the potato is moving when it leaves the barrel. And if you look at this, if you look at velocity is equal to the spring constant over mass square root times the distance compressed, you start to figure out that velocity can increase whenever k is increased, because this will get bigger, or whenever your mass is decreased. So a decrease in this will make this entire thing bigger. So those are the variables along with velocity. If you want a large velocity, you increase k, you decrease your mass. If you want a smaller velocity, then you decrease your k and you increase your mass.